Yeah, that's what I thought too, but I didn't. I like it, and then I got.
Up the events.
Kind of,
Or
it's the span of the airflow.
bottom pressure cook. See, have a good day, pressure, see you.
You guys have a good day.
Bottom pressure cook.
Hello, Dr. Chan, can you hear me?
Yeah, I can hear you.
Sounds good. So Dr. Chan, do you mind if I share my screen?
Sure. And let me enable it. Need to stop sharing on mine too. All right, what's up?
Thank you, sir. I just found a slight error on the syllabus, and I'm wondering if you could correct it so I could plan accordingly.
Sure. What is it?
Um, let me see. Right here. Do you see final projects due December 20th?
Oh, I apologize. Yeah, obviously it's not due in December, so it's going to be on May. I think I had the final due date up there, but I think it's like May 22nd or something like that.
It's all good. It's not a serious error, so that's all good. I was going to say, are we scheduled to get activity 5 today or on Wednesday?
Yeah, we're gonna do activity 5 on Wednesday. So today
Okay.
we're gonna do kind of the prep lecture for it. And then we'll
Okay.
do activity 5 on Wednesday.
Sounds good. Thank you, sir.
Yeah. All right, it's 7 o'clock. Let's go and get started. All right, good evening, everyone. Welcome back from spring break. How's everyone doing today? Good. All right. So I graded your guys' midterm projects over the spring break. So I apologize. I meant to finish them a lot sooner, but I had some kind of personal things happen over spring break. So I didn't finish grading them until Saturday. So your grade should be on Canvas, and so you should be able to view the grade. And I posted your rubrics as well. So for a lot of you, I left a lot of, I tried to be as detailed as I could be with my feedback. And so definitely read the rubric and so see kind of where you scored and kind of where you missed points. You know, the idea with the feedback that I gave you is that, you know, you should apply that towards your final project, right? So I know before the spring break, I promised you guys that I would have the final project ready by today. Obviously it's not, you know, I don't have it today, but it will be ready by Wednesday. So yeah, I apologize. You know, I'm still kind of catching up on some stuff just because yeah, I had some things happen over spring break. Okay. So yeah, so the final project, you know, just kind of in short, it'll be very similar to your midterm project. Thanks, Ismail. Yeah, it'll be very similar to your midterm project. And so, you know, a lot of the feedback that I gave you for the midterm project is going to be, you know, directly applicable for the final project. It's just there will be kind of some added components to the final project. And so basically the structure of the class from here on out is that, you know, we're going to be covering 4 more ANSYS activities. And so we have activities 5, 6, 7, and 8. And each of those is going to teach what I consider to be, you know, a more advanced feature in ANSYS. And so for your final project, you're going to be basically doing another finite element analysis. You're going to be writing a report, but you're also going to be incorporating 2 of these advanced features. And so this week we're going to be going over transient simulations, and so we go over kind of dynamics and what that means. Next week we cover optimization, I believe. And then we'll cover buckling and some other stuff as well. So the idea is that for your final project, you know, you incorporate some of these more advanced features, as well as a couple other extra requirements as well. But yeah, so I'm still working on the specifications and the instructions for the final project, but we'll talk about that. We'll see if we have time Wednesday. You know, I kind of want to devote Wednesday to make sure that we cover all of the, or we have enough time to do as much of the activities as possible. So maybe we'll talk about the project on Monday. Okay. All right. So I think that's all my announcements. So yeah. So again, so for today, you know, we're doing a kind of a prep lecture, and so today we're going to cover just kind of the basic concepts that kind of preps you for the activity Wednesday. Wednesday we'll do our activity, okay, and then we'll go from there. All right. Any questions I can answer before we get started for today? Okay. Okay, so let's go and get started. So the subject for today is going to be dynamic FEM simulations.
Oh, Dr. Chan,
Yes.
I know you're very busy and I don't want to come across the wrong way, but do you know when we will get the grades for assignment 4 or?
Yeah, so I'll try to grade those before the end of the week.
Okay, I just don't want to rush you or anything. I was just wondering.
Oh, for sure. Yeah, no, I understand. So yeah, I am a bit behind on stuff, but yeah, I'll do it by the end of the week.
No, it's because you have mentioned everything else, so I was like, did he forget about grading assignment 4, or I don't know if you forgot or not, so that's why I'm bringing it up.
Oh, for sure. Yeah. I just yeah, I'll do it end of the week for sure.
Sounds good, sir.
Okay. All right. So dynamic FEA simulations. So this is actually quite a bit of a large topic in general. So you know, in truth, you know, what we're covering in this class is a very, very small slice. And so it's very much from I would say from like a user's perspective. So, you know, just, you know, you want to learn as little as you want to just to run a dynamic simulations. That's kind of the approach that I'm taking. But in reality, you know, there's a lot of theory and there's a lot of kind of concepts that go behind this, but they're usually actually not taught in an FEA class. So if you're interested in learning more, you know, a lot of this theory is covered in kind of a more general numerical methods course. And then we do have a course like that here as well. So I believe it's EGGN 403. Okay. But just like the name implies, when we are when we're running dynamic simulations, we're going to be simulating a situation that changed with time. Because if you've noticed, all the simulations that we've done so far, they've been just purely static, right? And so we have our boundary conditions, we have our geometry, we apply all our modes, and we get kind of one, you can almost say snapshot, okay? So the main difference here is that, for static situations, you essentially just run one simulation, right? So you apply everything and you run it through the FEA solver once and you get one result, right? So you get one result field, okay? For a dynamic simulation, because things change with time, you're going to be running essentially multiple simulations, okay? Sometimes hundreds, oftentimes thousands of simulations. Okay. And so that's kind of the first thing that you'll kind of notice when you're running dynamic simulations, that the cost is significantly higher. Oftentimes thousands more than a kind of a comparable static simulation. Okay?
Dr. John.
Yes.
And that is because the equations take into account time, right? Which obviously get much more expensive.
Correct. Yes. And so because things are changing with time, you can almost imagine it like comparing a picture to a movie. So when you have a single image, that can capture like a static situation. But if you want to capture on video something that's changing with time, you have to capture, you can almost think of it as multiple images, right? And so
I see. That's a good way to see it.
Right. So you can almost think of a movie as kind of a collection of images that are all just separated by a small amount of time. And so,
the same concept apply, but with simulations.
Exactly. Right.
Very nice. Thank you, sir.
Mm-hmm. But and that's a good analogy for the results too. Well, it's not an analogy. That is the results. And so the result of a dynamic simulation is going to be an animation. So I think that part is really exciting to people. Is that you actually get to see something kind of change and move. So it's kind of a, it's kind of a an interesting topic. And there's, like I said, there's a lot to cover here, but we're just going to cover kind of the basic concepts, the basic intuition, just enough to learn how to get one off the ground. Okay. But there's, obviously a lot more to learn about this kind of stuff. Because if you want to learn more about the methods, and I even actually, I think you mentioned this before too, these kind of class of methods that's used to solve unsteady problems are called time marching schemes. So this is where your explicit, implicit kind of differences come into play. And so, we'll talk about those a little bit, just because it's important to know kind of the difference between some of the tools that are available in ANSYS. But from a theoretical perspective, from a conceptual perspective, we're not going to get into time marching schemes. That's a whole nother class. But we are going to cover the basics. So today's lecture is going to be split into two. And so on the first hand, we're going to cover what I consider to be kind of important, just kind of conceptual information in general to know about dynamic systems. And then we'll talk more specifically about what tools are available in ANSYS and what the differences are between. Okay. Any questions on this in general? Okay. And so to kind of give us some intuition in terms of, in terms of how dynamic systems behave, let's talk about lumped mass models. Okay. And so a lumped mass model is something like this. And so it's basically a mass spring damping. So there's lots of different ways to draw it. But they all kind of essentially have the same quantities. So it looks something like this. Okay. So we have three components here. We have a mass at the end, so we'll call that M. Okay. We have a dash pot, and so that represents damping in the system. So we'll represent that with a variable C. And then we have a spring that is kind of storing kinetic energy here as potential energy, and so we'll call that K. Okay. So this here is the spring. It's here. It goes by a lot of different names, but usually I call it like a dash pot. Okay. It just adds some kind of friction or some kind of damping into the system. And this here is our mass. Okay. So to excite this system, what you would do is you would pull on the mass, or you could push it, same thing. Okay. Displace the mass by a certain amount, and then you would let it go. Okay. So when the mass is pulled and released, what occurs here, and this is for the case if you have an underdamped system, what occurs here is underdamped oscillations or damped oscillations. It looks something like this. And so we have on the horizontal axis here, we're going to have time. And on the vertical axis here, I'm going to have the position of the mass. Okay. So we'll call that X, right? And so if we start, let's say that we start with kind of initial displacement. And so we start off with the initial displacement up there, okay? And we release it, the position of the mass would look something like this. And so it's going to oscillate. It's going to oscillate back and forth, but eventually the amplitude of those oscillations are going to decrease. Okay. And so in other words, system will vibrate due to the elastic properties of the spring. But those oscillations will die down because of the damping. Okay. Okay, so why am I bringing this up? And so, this is something that's covered in, I think, a lot of, science and engineering courses. So the reason I bring this up is that, before the age of high power computers, this simple mass spring system is how, engineers design dynamic response. Okay. And so they use this kind of simple system as kind of a model for how things like bridges, things like buildings will respond to dynamic mode. Okay. And there's a lot that you can pick up from here, and a lot that you can apply it to kind of a more complicated systems to give you a lot of strong intuition for how they behave dynamic. Okay. Because if you look at, the main quantity here is that the horizontal axis here is time, right? And so, if, vibration, you can almost think of it as kind of a change or a changing response with time. Okay. Okay. Any questions on this so far? Okay. All right. And so, this simple system right here and kind of knowing the response, we're going to draw a lot of analogies, right? And so the first thing we're going to say is that, the characteristic of the oscillations depends very strongly about the properties or on the properties of the physical system. Okay. All right. And so, by physical properties, what I mean is the spring constant, the dash pot, and the mass. Okay. So let's go over each one and let's talk about kind of what effect they have on the dynamic response. Okay. All right, so let's go over the mass first. All right, so the mass here represents the amount of inertia the system has. Okay. And if you recall, inertia is this property that makes it so that it makes it more difficult. The higher inertia that you have, the more difficult it is to change your state of motion. Okay. And so if you look at a massive boulder, right? So a massive boulder has a massive amount of inertia because it has a ton of mass, right? And so it takes a lot of work to get that boulder moving because it's so massive. Okay? At the same time, if that boulder is hurtling towards you at 60 miles an hour, it's going to take a massive amount of force to change its momentum because it has so much inertia. Okay. And so generally speaking, the more mass the system has, the lower the frequency of the oscillation. Okay? Because what's happening when the system oscillates, goes from one peak to the other. Another way that you can look at that is that it's a change in its motion, right? So it goes from one direction to the other, one position to the other. Okay? So the more mass you have, it's going to reduce the frequency of oscillation. Okay? And so engineers use this fact. And so they kind of knew this relationship that kind of the more mass of the structure that we have, the lower its frequency of response is going to be. Okay. And generally mass is easy to measure. Okay? Even for a complicated structure. And so, even for, something that you work on for your projects, right? All you would have to do is you would just take the volume of the structure and you multiply it by the density. Okay? So mass, or even more physically, if you have a scale that's big enough for your structure, you just weigh it on the scale. So, mass, something that was not too difficult to measure, and it was very well documented in terms of what effect it has on the dynamic response. Next, we have the spring constant. And so the spring constant represents how stiff the material is. Okay? Oops. So the spring constant represents the overall stiffness. So the higher your spring constant, the more stiff your structure is. Okay? And generally speaking, the higher your stiffness, the higher your frequency of oscillation is going to be.
Dr. Chan,
Yes.
does high stiffness mean less deflection?
Generally, yes. And so, the quantity in a lot of structures that kind of gets directly correlated with the spring constant is the Young's modulus. And so the higher your Young's modulus is, the more stiff your structure is going to be, right? Just because your material is made of a stiffer material. And so if you have a higher spring constant, or excuse me, if you have a higher Young's modulus, that means less deflection, but that also means, higher response frequency.
I see. Sounds good, sir.
And so while not as easy to measure as mass, because usually for, even for a complex structure, you have kind of a exact number for the mass. And that's usually not too, it's not too different from reality. It's hard to look at a complex structure and say to yourself, what the spring constant of that material, of that structure is going to be. Okay? Because it depends. It depends strongly on the material that you use for the structure. It's also going to depend on the geometry of the structure as well. But, with that said, generally we can get a good kind of, I'd say, qualitative sense for what the spring constant of stiff material is. Okay? And so it may not be as easy to measure as mass, but generally we can get a good feel for it based on the material properties and based on the geometry. Okay. All right, and so the third property that we have here is, of course, the damping. And so the higher the damping, or first of all, what the damping represents is that it represents any kind of friction or air resistance in the structure that can be used to basically sap away energy. So basically any place where you have any kind of inefficiencies or any places where you can kind of lose energy, that gets put into the damping.
Um, Dr. Chan, the damper is meant to eliminate all the extra energy, right? Or no? Or is that
Exactly. Yep.
okay? Okay, sounds good.
So the two most common examples of damping that you see in dynamic systems would be things like friction, things like air resistance. All right, so just like what was said, the damping, its purpose is to basically suppress or kill down the oscillations. The more friction, the more air resistance, the more kind of inefficiency that you have in your system, the more quickly your oscillations are gonna die down. Okay. So the damping is important, and in fact, the damping is a very important part of a lot of dynamic systems, and their performance actually depends a lot on how much damping you have. And so think of something like the shock absorbers in your car, right? And so the shock absorbers, its main goal is to basically act as a giant dam. So you run over a speed bump, and then what's preventing your car from kind of, hopping up and down is the damping that's in your shock absorbers. Okay. Unfortunately, because a lot of the sources of damping, at least all the unintentional damping, comes from things like friction, air resistance, geometrical irregularities. This becomes very difficult to measure. Okay. But in most practical situations, the damping is going to be there to some extent. Okay. Depending on the situation, you may be able to neglect it to a certain degree because the damping is so small, but eventually everything gets kind of damped down. There's no such thing as an infinite oscillator, right? So eventually everything has to die down eventually. Okay. All right, any questions on this? Okay. So again, the reason I'm kind of bringing up these three properties is that every dynamic system, at least on a structural sense, you can kind of, think about these three properties. Okay.
Dr. Chan, I do have a question.
Sure.
Can you scroll up?
Yes.
So can you go down? I want to see the three terms right there. Okay, so we have mass, spring constant, and damping, right?
Yes.
My first question is, which value do engineers play with the most?
Well, I mean, a lot of times you don't have that much control over some of these things, especially things like the damping. And so, I would say the ones you have the most direct control over would be like the mass. And so
yeah, because
oh, go ahead.
The mass is easy. Right, so that's something that engineers could play with. Can engineers play with the spring constant?
Yeah, you could. And so you can change the material. And so you can, you can use different materials that are stiffer, or maybe less stiff, depending on what you need. And stiffness also depends on geometry too. So like the overall dimensions of the structure, that's gonna affect the stiffness, the overall stiffness as well.
No, and then the damping would be just adding extra parts to eliminate or suppress any energy.
Yeah, you can do that too.
Okay.
You can also do things like lubrication, and so that's going to reduce any kind of friction, or maybe use a rougher material to add some friction, add some damping to the system as well. So yeah, it's harder usually to modify the damping, but there are ways that you can do that as
well. So adding more mass lowers the frequency of oscillation. Adding more stiffness results in higher oscillations, and then damping obviously suppresses it.
Yes, exactly.
I'm just trying to make sure I understand all this because I had an interview and they actually asked about all this. So
Oh, really?
and
Okay.
yeah, and I wasn't prepared, but now it's gonna be ingrained in my mind.
Okay, that's good. That's good. Yeah, once it's like one of those, you get asked it in an interview and then you kind of just know it from life after that.
Yeah, exactly. Thank
No,
you,
these
sir.
are good. Yeah. And so, all dynamic systems, they have these properties to some degree. So when you're thinking about, how is my system going to respond dynamically to a certain event or to a certain stimulus, if you think about these three properties, that already kind of gives you a lot of information, at least qualitatively, in terms of how the system will respond. Okay? Right. So when we do our activity on Wednesday, it's useful. So, we're basically going to be doing, a system with an impulsive loading. So we're going to be simulating a car crash essentially. And so what you'll see is that after the car crash, or after the car crashes into the wall, you're going to see an oscillating response. Okay. And so I want you guys to think about, what is the mass of this car relative to its stiffness based on its material, where are the sources of damping, are they significant? And how that affects kind of the dynamic response. Okay. Because when you talk about structures in general, you're often worried about kind of vibrations and resonance and things like that. So getting a good sense of this damped mass spring oscillator, already kind of gives you a lot of strong intuition. Okay. Of course, there's a lot of details that have to be filled in terms of what's considered a massive system, what's considered a stiff system. Is there a golden ratio between mass and stiffness? And so, a lot of those details kind of get filled in through experience, but it's I'm giving you kind of this framework here to kind of think about, because, most dynamic responses kind of get, applied into this framework. Okay. All right. Any questions on this? Okay. All right, so that's kind of a good, I would say, kind of introduction to kind of dynamic responses in general. Let's talk about how ANSYS specifically does it and what the differences are between their tools. Okay? All right, so we're going to be talking about numerical solutions to dynamic problems. Okay, so ANSYS basically has two different methods for doing this. One is called basically transient structural, and the other one's called explicit dynamics. Okay, so a lot of people see those two things, and you may wonder, what's the difference between those two? Okay, for the user's perspective, sometimes there is no difference. So for a lot of problems, both are going to be working on the same. But there are some kind of more subtle differences in terms of, what are some situations where one might work better than the other, and so on and so forth. But before we get there, I am kind of getting a little bit ahead of myself. Let's talk a bit more about, in general, how do we actually get numerical solutions to these problems? Okay. So compared to static problems, compared to static problems, dynamic problems are going to have significantly higher cost. Okay? Okay. And remember, what I mean by cost here is that I mean things like, computer memory, things like time. Okay, so it's going to take a lot longer and a lot more computer resources in order for you to solve. Okay. And so just like I mentioned earlier, the reason for this is that, a dynamic solution or a dynamic simulation is essentially a series of snapshots or a series of simulations that are stitched together into an animation. Just like I mentioned before, when I say that it's basically an animation, sometimes they're going to require, hundreds or thousands of these simulations can be stitched together. Okay? So you're talking about a cost that's, 100 or 1,000 times at least compared to a static simulation. And of course that adds up. Okay. And so the biggest difference here is that, when you're talking about dynamic problems, not only is position going to be an important variable here, but now time is a variable as well. And so, you may be looking at that and you might be saying, that's just an extra variable, right? But time behaves very differently than space, because time is what's called, what we call is causal. And so what that means is that time, you can't solve for something, so far into the future. Okay? You have to solve for something in the present first, and then you have to kind of solve sequentially from. And so each moment in time, depends on the moment preceding it. Right? Sounds something that's more profound than it actually is, but each word that's coming out of my mouth, right, each word that I'm saying depends on the word that I said previously. Okay? That's just how time works. Space works differently because, because of the way things kind of change in space, if you're solving for, the solution in a structure, we can kind of solve for the solution in all kind of space variables at the same time. And that's essentially what we're doing in our static simulations. But time isn't like that. Okay? You can't move on to the next time step until you solve for the current. Okay. And so this gives rise to something called our time marching schemes of time integration. Right. So we're not, like I mentioned, we're not going to go over the details of what a time marching scheme is or how that works. That's a subject for a different class. We're just going to go over kind of the basics of it. Okay. So the most important thing to know about a time marching scheme is that you have to specify a time step size. And so what the time step size represents is that it represents kind of the amount of time in between each successive frame in your animation. All right, so if we look at a timeline here, if we're solving for the solution in time, when we apply a time marking scheme, we are solving for the solution at discrete points in time. Okay? And so we're basically looking at snapshots of the solution at different points in time. And so the time step size, very much like your mesh grid spacing, is the amount of time in between each of these grid points. So it's going to be delta t, delta t, delta t, okay? So on and so forth. It's time step 1, 2, 3, 4, 5, 6, 7. Okay. And each of these time points here is a separate simulation. And intuitively, you can think of the time step size very similar to how you think of the mesh grid spacing. Okay? And so generally, what we've kind of established in the class so far is that the smaller you make your elements, the more accurate your simulation is going to be. Okay? Same thing for this time step size. And so the smaller you make your time step size, the more accurate your dynamic simulation is going to be. But, just like the mesh grid spacing is that the smaller you make your time step size, the more expensive your simulation is going to be as well. And the reason for that is that, each dynamic simulation, at least the way that it's set up in ANSYS, different softwares use different methods. So actually, I'm more used to a different method. But the way simulations work in ANSYS is that you have to specify what's called an end time as well. So in other words, you have to specify how long or how much time that you want to simulate for. Okay. And so, for example, let's say that you are simulating a phenomenon that is going to take 10 seconds. Okay. And so your end time there would be 10 seconds to make sure that you capture, all 10 seconds of whatever action is that you're trying to simulate. Okay. And so this is not the amount of time that you want the simulation to run. No, your computer kind of decides that. Your computer decides how long it's going to take. But for your animation, or for how long your simulation itself is going to be, that's your end time. Okay? That's a terrible example, but you get the idea, right? And so, however long your phenomenon is going to take, you want to make sure you specify that in your end time. Okay? So for, this is a better example. So, for activity 5, we're going to be simulating a car crash. Okay? We're going to start the simulation basically right before the car makes contact with the wall. Okay? And what we're going to simulate is basically the car kind of, hitting the wall, making contact and crumpling up, and then, and moments after that. So actually our end time there is going to be very, very small, because that takes place over a very short period of time. So what you'll see on Wednesday is that our end time is going to be something like, a couple milliseconds, something like that. Okay. And so now that we have our time step size, and now that we have our end time, we can compute the number of time steps that we are going to simulate, or that we need to simulate. Okay? So you can almost think of this as the number of simulations that you're going to run in your dynamic simulation. So we'll have n is equal to the end time, we'll call that big T, divided by the time step size. For example, let's say that we want to run a simulation where our end time here is 10 seconds. Okay. And so it's going to take 10 seconds in order for us to fully simulate whatever we want to simulate. And we want to do this with a time step size of 1 millisecond, so 0.001 seconds. Okay. That means our number of time steps or the number of simulations that we need to run is 10 divided by 0.001, which is 10,000 time steps. So in order to properly simulate this dynamic response, we need to run essentially 10,000 simulations, which is a lot. And if each simulation there takes, let's say, on average, maybe it takes maybe 20 seconds. And so you have 10,000 time steps times 20 seconds. And so you can see the cost, will really add up very, very quickly. All right, any questions on this? Yeah.
To making the time steps smaller doesn't necessarily mean the accuracy is down. It's just become.
Exactly. Yeah. Yeah. So there is a sense of like convergence for this as well. So there is kind of an ideal time step size where it minimizes the cost, but then it also gives you kind of the maximum accuracy as well. And then once you get past a certain point, reducing the time step size doesn't kind of give you any benefit as well. The difficult thing with dynamic simulations is because they're so expensive, it's really difficult to get to do a convergence test for time step size, because a lot of times your dynamic simulation will run like for hours. And so usually it's not worth it to run multiple of those to get the ideal time step size. And so what a lot of people end up doing is that they kind of do it by feel. And so once you kind of work in the field or work in a certain kind of area for a while, you kind of get a sense of like 1 millisecond will be good, or a tenth of a millisecond will be good, and you can just kind of use that for most of your simulations, and then you adjust it if you need to. All right, any other questions on this? Okay, all right, so let's get to the part where I thought we were going to. Let's talk about the difference between the two main tools in ANSYS, which is transient structural and explicit dynamics. So these two are the main tools that you have available in ANSYS for simulating dynamic situations. Okay. So on the surface, and you could try both. And so, if you want on Wednesday, you can definitely try the other. The one that we're going to be using is explicit dynamics, but if you want to try out transient structural, the setup is very, very similar. Okay. So on the surface, these two, on the surface, these two look like they're almost, basically exactly the same. The setup is almost exactly the same. Okay. Their main difference lies in how their schemes or how their time marching schemes are implemented. And so, of course, we don't have enough time in this class to kind of discuss kind of the finer details of their differences, but it is good to kind of talk about them kind of in general. So what are some situations that work well for transient structural versus what are some situations that work well for explicit dynamics? Okay. So the main difference, at least from a user perspective, that you have to know, has to do with how strict you are in terms of the time step size. Okay, so transient structural. Transient structural implements what's known as an implicit time marching scheme. And so what an implicit method basically allows you to do is that it allows you to be a lot less strict about the time step size. And so you could, and so if you're using transient structural, you could set the time step size to be something fairly large, something like maybe like up to even a second, and you'll still get a decent solution. Right? The reason for this is because for an implicit method, you have something that's called, it's not fully guaranteed, but it's almost guaranteed. You get guaranteed stability. And so stability, basically what can happen sometimes if you're running an unsteady simulation, if you're running a dynamic simulation, is that the entire simulation can just go, how should I say, the entire simulation can just go crazy. Hey, because things are changing with time, sometimes if you're not careful with the time step size, you'll get results that are just not physical at all. And so you'll get deformations that are like 10 times 10 to the 16th power, something like that. So so when you get something like that, then you have an unstable solution. But if you're using transient structural, which uses an implicit method, then you're almost guaranteed stability. Okay, so that's a very powerful thing, because then you can set time step sizes to be very large. The downside to transient structural is that on a per time step basis, so each time step that you simulate, so each simulation that you do is a lot more expensive. Okay. So when is transient structural good? So transient structural is good, when you have a situation where you need to set the end time to be high. So you have something that changes over a long period of time. So in these situations, where you have to, where you have kind of these slower changes, you want to set a larger time step size because, you don't want to simulate a ton of time steps. So let's say that you're simulating something that's going to change over the course of a minute. So that's 60 seconds, right? If you're simulating a dynamic response that's going to take 60 seconds, you want your time step size to be something on the order of, maybe something like, at least maybe like 50 milliseconds, something like that, okay? Because you don't want to be simulating, millions of time steps because then, you're going to be there forever. So in those situations where you have something that changes slowly, I would say that's something that's used for transient structure. Okay. So in situations where you want to kick up the time step size as much as possible, transient structural is good. So on a per time step basis, it may be more expensive, but it helps get you to those higher time steps, higher times a lot more easy. Any questions on transient structural? Okay. All right, so let's talk about explicit dynamics. And so this is the one that we're going to be using on. This is the one that we're going to be using on Wednesday. So with explicit dynamics, this implements an explicit time marching scheme. And so the big difference between explicit and implicit is that, you have to be a lot more strict with your time step size for an explicit scheme. And so with explicit dynamics, you're not able to set the time step size to be too large, because if you set the time step size to be too large, then what can happen is that your simulation can become unstable. And an unstable solution is a useless solution. So, it doesn't matter, how well you set up everything else. If your solution is unstable, then you're basically just getting garbage numbers. So, instability is something that you want to avoid at all costs. Okay. So you may be wondering, then why would we ever use an explicit time marching scheme? So if an implicit scheme, there's, we don't have to worry about stability, what are the upsides? The upside to using an explicit scheme is that each time step that you do simulate is a lot cheaper. It's hard to put a number in terms of, exactly how much cheaper it's going to be compared to the implicit scheme, because a lot of it depends on your mesh, it depends on your geometry, depends on your loadings and things like that. But generally, you can expect it to be, anywhere on the order of at least twice as fast to up to 10 times as fast. That's generally kind of what I see. Okay. And so even though, essentially what you're going to have to do for explicit dynamics is that you're going to have to simulate more time steps than the implicit counterpart, but each time step that you do simulate is going to be a lot cheaper. Okay. And so when would you want to use explicit dynamics? Okay. And so because we have such a strict requirement on the time step size for explicit dynamics, these are best used for situations where you want the time step size small to begin with. Okay. And so situation that's going to happen very, very quickly. And so in order to capture the full response, you need your time step size to be small anyway, otherwise you're going to miss something. Right? And so one example is a car crash, right? And so because things happen so quickly in a car crash, in order to make sure you get all the data that you need, you're going to want to set the time step size smaller anyway, right? So, even forget about instability, just to make sure that your simulation actually captures everything that it needs to, you need to set the time step size smaller. So in those situations where the time step size already has to be small, you might as well use explicit dynamics where it's going to be a lot cheaper for each time step. Okay. All right. Any final questions on this? Okay. All right. So in a nutshell, that's basically the big difference between those two. Okay. So we're gonna be using explicit dynamics on Wednesday when we do our activity. And that's going to give us, probably going to be our best results. But if you're curious, you can try the exact same simulation under transient structural and see how that works. Okay. Okay, so that's all I got for today. So let's go ahead and end a little bit early. So thank you guys for coming today. Hope you guys have a good rest of your evening, and I will see you Wednesday for our activity.
Thanks, Professor.
Thank you, Dr. Tron.
Thanks, Ivan. Have a good night.
You too, sir.
Yeah, see you Wednesday. Ahmed, any final questions? All right, I'll see you Wednesday.